Look up at the night sky, and you're not just seeing a tapestry of distant stars. You're looking at an archipelago of untapped wealth, a sprawling frontier of raw materials, drifting silently through the vacuum of space. How do we transform these primordial remnants of the early solar system into the foundational bedrock of a multi-planetary economy? The answer lies at the razor edge of modern orbital mechanics and robotic engineering. We are standing on the precipice of a new industrial revolution, one where the factories and mines are suspended in zero gravity millions of miles from Earth. Asteroids are the leftover building blocks of our solar system, ancient rubble that never managed to coalesce into a planet. For decades, these celestial bodies were viewed primarily as scientific curiosities or existential threats. Today, we embrace a radically different paradigm, viewing them as the ultimate supply depots for human expansion. According to data from NASA, the asteroid belt alone contains enough mineral wealth to fundamentally rewrite the economic realities of our species. But extracting these resources requires overcoming some of the most punishing physical environments ever encountered. The orbital prize is divided into three distinct geological targets. Near-Earth asteroids are classified based on their spectral composition and internal makeup. C-type asteroids are carbonaceous, meaning they are rich in clay, silicate rocks, and most importantly, water. S-type asteroids are stony, composed of silicate materials and nickel iron. Finally, there are the M-type asteroids, the metallic behemoths. These dense metallic cores of shattered planetesimals are heavily enriched in platinum group metals, a suite of elements critical for advanced electronics, green energy technologies, and catalytic converters. The economic rationale for pursuing these orbital quarries is driven by the staggering cost of launching mass from the surface of Earth. The tyranny of the rocket equation dictates that escaping Earth's gravitational well requires exponential amounts of fuel for every kilogram of payload. If we want to build massive orbital habitats, sprawling solar power satellites, or deep space generation ships, hauling every steel beam and gallon of water up from Earth is financially ruinous. By harvesting materials that are already in space, we bypass the deepest gravity well in our immediate cosmic neighborhood. Reaching these targets is a masterpiece of celestial choreography. Asteroid mining operations begin with the brutal mathematics of orbital mechanics, specifically a metric known as delta V. Delta V is the change in velocity required to perform a maneuver in space, effectively acting as the cosmic currency of orbital travel. Surprisingly, reaching certain near-Earth asteroids requires less delta V than landing on the surface of our own moon. By carefully timing launches to align with an asteroid's orbital trajectory, spacecraft can intercept these bodies using highly efficient propulsion systems to cross the vast interplanetary voids efficiently. Future mining vessels will likely rely on solar electric propulsion, commonly known as an ion drive. An ion drive works by accelerating charged particles using an electric field, producing a gentle but continuous thrust that builds up massive speeds over months or years. While chemical rockets offer a brief violent explosion of power, ion thrusters provide the sustained, fuel-efficient marathon running required for heavy industrial hauling across the inner solar system. Arriving at the destination only begins a marathon of physical challenges. Upon rendezvous, the spacecraft must match the asteroid's velocity and rotation, engaging in a delicate orbital dance with a tumbling mountain. The gravitational pull of a typical near-Earth asteroid is practically negligible, creating a unique nightmare for heavy machinery. You cannot simply land a massive drill on the surface where the escape velocity is measured in centimeters per second. The moment a conventional drill applies downward pressure, the equal and opposite reaction would instantly launch the mining rig back into the void. To achieve this extraction, those microgravity mechanics force a complete reimagining of industrial equipment. Instead of relying on weight to provide traction and stability, robotic miners must actively anchor themselves to the celestial body. Engineers propose deploying harpoons, microspine grippers, or even drilling augers that secure the spacecraft directly into the regolith, the layer of loose, fragmented rock and dust covering the asteroid. Only once firmly tethered can the actual extraction begin, turning the spacecraft and the asteroid into a single unified mechanical system. For the water-rich C-type asteroids, extraction relies less on brute force and more on thermodynamics. The primary technique proposed for these bodies is volatile heating. By enclosing a section of the asteroid in a massive sealed canopy, we can focus concentrated sunlight using massive orbital mirrors. As the surface temperature rises, the water ice trapped within the porous rock undergoes sublimation, transitioning directly from a solid into a gas. This vapor is then captured, funneled into cold traps, and condensed back into pure liquid water. The physics of sublimation in a vacuum provide an elegant solution to an otherwise messy problem. There is no need for heavy crushing equipment or complex chemical solvents. The sun does the heavy lifting, baking the precious volatiles out of the ancient rock. This captured water is the absolute bedrock of the future space economy. In orbit, water is far more than just life support for astronauts. When subjected to electrolysis, water separates into hydrogen and oxygen, the exact components of high-performance rocket propellant. That localized propellant production is the key to unlocking the wider solar system. By converting C-type asteroids into orbital gas stations, deep space missions can launch from Earth with relatively empty tanks, saving upwards of $1.5 billion in launch costs for large-scale expeditions. They simply dock at an asteroid-derived depot, fill up with extraterrestrial hydrogen and oxygen, and ignite their engines for Mars, Jupiter, or beyond. The economic paradigm shifts from Earth-dependent supply chains to a self-sustaining infrastructure built entirely off-world. Mining solid iron and platinum from M-type asteroids requires a vastly more aggressive approach than baking out water vapor. For these dense bodies, mechanical excavation is unavoidable. Robotic trenchers and bucket wheel excavators, redesigned to operate without the benefit of gravity, must scrape and gouge the surface. The resulting debris, a chaotic mix of valuable metals and useless silicates, floats freely in the microgravity environment, presenting a massive containment and sorting problem. To separate the wheat from the chaff in zero gravity, engineers will utilize magnetic separation and electrostatic sorting. Because the target metals are highly conductive or magnetic, passing the pulverized regolith through powerful electromagnetic fields allows the valuable ore to be pulled from the sterile rock. The waste material is vented back into space, while the concentrated metallic dust is gathered for the next, and perhaps most difficult phase of the operation. Extracting the ore is useless without in-space processing. Raw metallic dust cannot be easily manufactured into satellite components or habitat bulkheads. It must be smelted, refined, and alloyed. Yet the very concept of a foundry relies entirely on Earth's gravity. On our home planet, molten metal separates naturally, with heavier elements sinking to the bottom and lighter slag floating to the top. In orbit, molten metal forms a floating, bubbling sphere where impurities remain stubbornly mixed within the alloy. Overcoming this requires the invention of zero-gravity refineries. Research published in materials science journals suggests utilizing centrifugal processing. By spinning the molten ore inside a heated, rotating drum, artificial gravity is induced, forcing the heavier elements outward while the lighter silicates pool in the center. Alternatively, advanced manufacturing could utilize the raw metallic powder directly, using high-powered lasers to sinter the dust into complex finished components right there in the vacuum of space. The economics of these metallic bounties depend entirely on their final destination. The overwhelming majority of iron, nickel, and aluminum extracted from asteroids will never see the surface of Earth. It is simply too expensive to bring them down. Instead, these base metals will feed orbital construction yards. They will be the girders of vast space stations, the hulls of interplanetary transports, and the shielding required to protect fragile human bodies from the relentless bombardment of cosmic radiation. However, the platinum group metals represent a different economic equation entirely. Platinum, palladium, and rhodium are incredibly rare in Earth's crust, yet vital for global industry. A single, modestly sized M-type asteroid could contain more platinum than has ever been mined in human history. The sheer value density of these elements makes them the only materials economically viable to return to Earth's surface. But safely dropping thousands of tons of precious metal through the atmosphere is a terrifying logistical hurdle. You cannot simply drop a solid block of platinum from orbit and expect it to land safely. The kinetic energy of an object re-entering Earth's atmosphere at orbital velocities is catastrophic. A raw, unshielded payload would either burn up entirely, scattering vaporized billions across the stratosphere, or impact the surface with the force of a tactical weapon. Returning the wealth of the solar system requires mastering the delicate art of atmospheric entry. Engineers propose utilizing a technique called aerobraking, coupled with specialized heat-shielded entry capsules. The refined platinum would be packed into automated blunt body pods. These pods would intentionally graze the upper edges of Earth's atmosphere, using atmospheric drag to bleed off velocity over multiple orbits. Once slowed to a manageable speed, the capsules would plunge through the thicker lower atmosphere, protected by ablative heat shields, before deploying massive parafoils to glide to a gentle touchdown in a designated recovery zone. The successful return of these capsules would trigger a seismic shift in global markets. An influx of cheap, abundant platinum group metals would crash their terrestrial commodity prices, fundamentally disrupting traditional mining operations on Earth. Yet this localized disruption would spark a massive boom in secondary industries. Cheap platinum means cheap hydrogen fuel cells, accelerating the global transition to green energy and potentially solving some of our most pressing terrestrial environmental crises. Building this orbital supply chain requires an unprecedented mobilization of capital and technological daring. It will necessitate fleets of autonomous prospecting probes, massive orbital tugs powered by next-generation fusion propulsion, utilizing the power of miniature synthetic stars to cross the void, and the development of robust artificial intelligence capable of managing complex industrial operations millions of miles from human oversight. The upfront investment will be astronomical, but the potential return is nothing less than the permanent economic liberation of the human species. We are transitioning from a species constrained by the finite resources of a single pale blue dot to a civilization with access to the infinite material wealth of the cosmos. The engineering challenges of capturing, drilling, and refining these primordial rocks are daunting, but they are not insurmountable. Every equation solved, every zero-gravity mechanism perfected, brings us closer to a future where the industrial heart of humanity beats in the silent vacuum of space. The era of purely scientific space exploration is giving way to the era of space industrialization. Asteroid mining is not a distant fantasy. It is a practical engineering inevitability driven by the cold, hard logic of economics and the unyielding human desire to expand. By reaching out and harnessing the ancient rubble of the solar system, we lay the indestructible foundations for a multiplanetary future, ensuring that humanity's story will continue long after we have outgrown our terrestrial cradle.